Okay, and the title of this is resistivity testing for grounding and corrosion control. And it's not resistivity imaging, as we focus on quite a bit at AGI. It's the same instrument, the SuperSting, but used in single channel or point measurements, and that's due to the protocols for these industries. And there has been quite a lot of interest in this because I think for a few reasons. It's critical infrastructure if you think about it. Grounding systems for towers, carrying power, telecom, corrosion control for pipelines, moving all sorts of products, subsurface tanks. And these corrosion control systems are energized sometimes. They pulse and they have a sacrificial anode. And so they need to be designed around the earth materials that they're installed in. So the precursor, the planning for a specific site would involve these tests. And if you already have a mini sting or a super sting system, let's see here. Okay. I think let me go back to the front screen there. Okay. Just had to change the view. At any point, this testing prior to the installation is very important, and there's different protocols for that. So I'll go into the basic theory of these tests and the field procedures, how to best do them. Get into things like heterogeneity or mixed earth materials and how those can be best accounted for. That was an important question. And different error codes and quality control and field data corrections and things along those lines. So hopefully now I'm sharing my screen. Again, if you're just logging in, there's a question window, and feel free to ask questions in there for the end of the seminar. Okay, so going to the next slide. This is just a little bit about myself. I've been involved in electrical geophysics my whole career in EM, and actually used AGI instruments a lot, especially at the USGS. So my background is broader, but now I very exclusively focus on electrical methods. Here's the agenda. Basic theory for Wenner. Of course, Schlumberger is just a slight change in the geometry, similar screens, field data collection procedures for all of this, how to avoid site issues. Sometimes you're given a line layout that puts you near ground and metallic infrastructure, how to suggest other positions that will give you the earth materials versus the earth materials mixed with that grounded metallic infrastructure, field data geometry errors typically, how to correct for those, and how to get the data you need quickly and efficiently, and automation versus manual comparisons towards the end. This is just the basic measurement. This is a Wenner array. It's showing A, B, and N. That's A and B are current 1 and current 2 on the outside of the array. This is a slice through the earth. And M and N are P1 and P2. And we're just using this circuit diagram to show you how we energize a potential field. You see the equipotential surface, those voltages sampled at the potential electrodes, and the current line. And this shape we see here is in a homogeneous space. And we'll get into how that's important later. But that's what we're doing. We're instantaneously measuring that potential field from those 4 electrodes. And that's the basic measurement. there. This is a different arrangement that's used for imaging, and I'll even show one of these and how it applies to grounding and cathodic protection. This is having the transmitter outside of the receiver, so more complete measurement of that potential field. And this is recorded, and all of these details you could get later. So I'm not going to get too much into that. This is these are the voltages. You can see these are very small. That's why our system needs such good isolation, and why we stress that in the design. The receiver is very sensitive, and the transmitter itself, on the scale of small testers, like the Megger or the some of these other small handheld ones, ours is a very large transmitter, 200 watts on the Super Sting, or 50 watts on the Mini Sting. But on the scale of some large geophysical systems, it's not. They're doing kilowatts, but we can still image deep, 500 meters with the Super Sting, because of the sensitivity of our receiver. So that's important to keep things smaller and safer, actually. This is the cable, the molded cable, and that's the stainless steel stake. For the grounding and FOP, you would be connected directly to the grounding grid, and your stake would not have that spring, but you would still want a point source. So you would clip off to the top with your wire. And then this is just 2D and 3D lines with the instrument on the ground. And I just was going to show this small generator, this Honda generator that you see there. That is lighter than deep cycle marine batteries, which is what the Super Sting runs on. So if you do have access to a small Honda generator, we have these generator power supplies that they're two yellow boxes. You can just barely see them off to the right here. That would run the Super Sting, and that whole system, it doesn't need to be recharged. It's a lot easier to use, and it'll run 8 hours on the small internal gas tank there. So that'll give you that full 200 watts of power. And this is quite, I'm sure this is familiar with you guys, just going into Ohm's law and related to that potential field diagram earlier, and how conductivity is reciprocal of that. This is the SI unit. We use ohm meter or even ohm feet, and that all of that can be changed on the instrument or converted later. But your basic measurement is resistance, V over I. And apparent, we call it apparent resistivity because it's based on this geometry for this space. So it's not a point. We also call that a pseudo plot point. That was back here. To get the true resistivity, you would either need a soil sample or to run a model, an inverse model. So this is a pseudo point. These measurements actually, even with the Wenner, here, the pseudo plot point would be in the middle, but it's incorporating information all the way around. And the last few slides in the presentation will address that. So now into the nuts and bolts of these surveys. Fundamental concepts: resistance versus resistivity. If you have the geometry, you can convert it to the unit material property with that unit. Resistance is not a material property. So knowing or having a good plan and tracking of where those electrodes were placed is very important. In some cases, the operators will put the stakes at the required position, but they'll annotate the spacing wrong. And if you were to plot all the data and then you see one outlier, sometimes it's very safe to say that you can correct that that spacing. The R1 or the R2 or the R3 or the R4. post-processing if it all lines up. That is something that I have seen happen before to get the correct resistivity with having the resistance and knowing where the electrodes should have been. And that's a disconnect on manual placements. And this is just putting it in context of 7 ohm meters is essentially a mineral water. That's a very low resistivity that you would see, say, in a fully saturated clay. In 0.25 ohm meters is pure seawater. So in the range of what you'll see with these instruments on these tests, you would expect not much more than below 1 ohm meter, and then maybe up to tens of thousands of ohms in very dry hard rock. And these are the dominant controls on resistivity. Number 1 being moisture content. So there are some sites where they do wet and dry season measurements, and that's a nice repeat project for these infrastructure type studies for a grounding grid to know how it should be designed for the full season. Porosity and permeability are stable in general. That's your secondary control. And then pore fluid, dissolved solids, that's on the order of fresh versus salt water. So your site's not going to change position unless you're tidally influenced or something along those lines. Temperature can be essentially removed unless you're down in the geothermal zone of things, very, very deep. Temperature can usually be disregarded. And then finally, the resistivity of the earth materials themselves. So you can see that if you're below the water table, if you know where the water table is, determining number 5 is much easier. You can disregard number 4 and number 3 most likely. So this is why resistivity is very good at determining geotechnical or geologic materials, the mineralogy. It's used quite often for that. And also for finding moisture zones for various reasons. Or for slope stability when things are compacted along those lines. And then this is these ranges, and you can see there's a very wide ranges between these rock types, and that has to do with saturation and mainly saturation and compaction and fractures. Like in limestone, they would tend to channel fluids and lower the resistivity. So there's a very wide range. So there's not one resistivity for a particular rock type. If you have a one drill core from a site, you couldn't really extend that out very far. And this geometric factor here, that is how we convert the V over I to resistivity. And that is for Wenner. It's a very simple one. You could do that in Excel. And this is the full formula in a 2π space for the electrodes at the surface. There are some other arrays that you can do. Wenner and Schlumberger are the ones most common for this resistivity testing. This is the vertical electric sounding that you're doing. And you can see that it's over a single point here. And that potential field would encompass this whole zone. So it's valid for this layer cake type model, and that's how the CDAGS software works. I've seen that at the CIATI meetings, and that's how people are modeling. That's one of the more popular software for modeling these grounding grids. Okay, that's the mini sting in the field. Quick picture of that, and that's the potential electrodes and the current electrodes and the operator in the middle with some cable reels. There's the Schlumberger array. This has less movements. You can stay in the middle at a particular MN spacing, say 1 here, and then have the 2 outer ones moved. So there's less total movements. Whereas in the Wenner, all of these spacings are equal. There's just one A spacing. So all 4 electrodes are moved on each position. So Schlumberger is a little easier regarding labor, slightly different protocol. This is our Earth Imager 1D software. It solves a best fitting inversion 1D solution to these pseudo data. That's our curve. In general, it should be smoothly changing as you get to larger spacings. And that's a good QC step, is to plot this on log paper or in software when you're on the field. And we're working on that for our app to give us this type of chart in real time. This software is very quick. It loads the raw data measurement from the super sting or the mini sting and gives you this plot. And you can go to the additional step of solving this layered resistivity model. I'll just show you really quick how quick that is. So if you had this on a laptop, you would point this towards a Wenner. That's a one. Oh, that's a straight one. There's a demo folder here. So there's a typical Wenner sounding, and then this is a 12-layer solution, which is quite a bit more than typically needed. But you can change that here, and you can lock different layers. You can a priori set thicknesses and layers if those are known. Typically, you would solve for about 5 layers, like that. And I'll go into this compared to 2D later, but that's a nice smoothly changing Wenner survey. Okay. These are our levels, our injected current, our measured voltage, what the sensitivities are, and when the software rejects low voltages. So you can see that we're injecting on the level of amps and up to 400 volts actually, and then our measured voltage is in the millivolts typically. So that's why the instrument is has to have an isolated battery, nothing else connected to it, or a nice generator like I showed earlier, and quality control of your cables. You know, keeping the insulation good on those will prevent noise. That's a relatively low-cost item to replace periodically. It's almost consumable. And then the coupling of, you know, it's the devil's in the details. I would say 80% of the noise issues that I see are related to the stake coupling to earth, and the electrical coupling there. Just a small amount of, you know, contact resistance is a major QC step, and that's why we added that to our latest firmware on the Super Sting screen. When you go to the Wenner manual, you'll actually see CR near the output current, because they're very closely related. If CR or contact resistance is lower, your impedance, the injected current goes up, and that's your signal. Of course, signal to noise is very important, the ratio. So having your field guys do something as simple as adding a small amount of water and tapping the stake in firmly makes a huge difference, especially in dry desert soils. Raising this injected current up is really good. That's important. Rain, not leaving. So the instrument runs, you know, these high signal levels, and it is hermetically sealed, but it's getting very hot. And if it's, you know, if it's rain, there's cold, there's condensation, there's all kinds of things. And there are desiccant packs inside the Super Sting and the Mini Sting. but they can get overwhelmed sometimes. So it's best to shield it from any type of rain and actually not work in the rain. We don't recommend it. But you can if you're really in a pinch. And also with hot weather, protect it from blazing sun. So you can see that screen. And yeah, of course, thunder and lightning have obvious issues. Leaving cables out overnight, the plastic is or wires is attractive to animals, so you'll need to watch out for that. And these are just the basic QC steps. The factory defaults for the Super Sting are to measure twice, so that you get a percent standard deviation error. If you were to bump up that number of readings for some reason, say to 10, some people ask this question, why it did not repeat 10 readings. And it has to do with where noise comes from in this method and what threshold you set for your error. So let's say you set something reasonable like 2% or 5%. If you set 0%, that is essentially nearly impossible unless the instrument is smoothing the result or is only reporting to a whole number for 0. There are some instruments out there that do that. Ours does not, and it uses a more rigorous standard deviation. So something on the order of 2% is reasonable for a clean site. And this noise is spurious. So if in the first 2 readings you achieve 2% error, it won't measure 3, 4, 5, 6 on up to 10 readings if you had manually bumped it up, because then you would be opening yourself up to more noise in time, since these voltage spikes are spurious, and over the course of 10 seconds you may get one. So it'll just stop and report the best data that it has gotten. Here's a picture of the Super Sting on the ground with some large cable reels. And a battery, and a hammer and some stakes. This is the general layout here. This battery is sitting directly on the soil, which is probably okay, but it's better to have it raised up because this looks like a wet cell. There could be something conductive coming out of it, fluids, and that would cause a ground loop. The negative post is actually a reference for all these measurements. So you don't want anything else connected to your battery or having it, any kind of conductive fluids leaking out or possibly conducting some straight current into the ground. There's a close-up picture of this is in the States, and one of our customers who really wanted to protect the wires, they do something that helps them go faster, where they actually drag the wires out. We would suggest playing it out, like a rope by hand, but that does take more time. So they added these wire they added the wires to this wooden lath so that it's a strain relief. And you can see everything is center referenced, and you're pulled out from the center here. And then they have their adapter box connected to the Super Sting. This is a basic walkthrough of how to run the the menu settings and all of that. This is also on our website, so I won't focus too much on the nuts and bolts. It's pretty straightforward. It's showing you your Wenner spacing, mentioning the isolated battery. You simply go to manual mode. If you want some higher level, there's a couple things you can't get directly off the screen. In some cases, the source voltage is required, and that's the voltage at the transmitter, and that's easily available from the data file. And you can just drop that into Excel or Google Sheets. I have an example here. I can email anyone who requests with the headers already. It's a human readable text file that comes out of the Super Sting, and there's a column here, HV, that gives you your transmitted voltage, and it's easy to plot the curve in this case. So feel free to request that as needed. This is our app screen for a Wenner sounding, and you can see this this one actually doesn't show CR, but it is, yeah, I'll double check on that and let you guys know. But we have apparent resistivity, resistance, the standard deviation, the number of cycles, transmitted current, the number of readings in this particular data file, the CD1, and the A spacing. And the A spacing and the resistance are the bare minimum, two things that you would need to process these data. This is the mini Sting instrument. It has, it doesn't have an app, but it has a similar screen. It has a small internal battery that will power it up to 15 watts. If you connect an external battery, it is up to 50 watts. So that's, it has a boost mode, so to speak. And that's the screen on the mini Sting. That's the current I, the delta V over I, the apparent resistivity, the N value, number of readings, and the error. Now for fall off potential, I'm just showing you the layout of that related to this adapter box that would be connected to the Super Sting. And you can see this the A and M, or the C1 P1, are jumpered together. In some protocols, they require you to run a separate wire out, but it's the equivalent to jumpering those two to connect to the grounding. It says grounding rod, but typically it's a grounding grid. And then having a rover potential electrode and a distant current electrode. And there's some geometry that would be given to you for a project like this. And it's to measure the grounding of a system already installed. And you would request that power be disconnected from it so that there's no leakage to the ground. You know, in some old grounding grids, there's some leakage to it. So this is side by side with the jumper between C1 and P1, or the wires going out. And these are equivalent to each other. Okay, just a second. Okay, I am keeping track of the questions asked so far. I just popped that window out, so I'll have it for later. Thank you, guys. Okay, so how am I doing for time? All right, just a few more nuts and bolts here. This is the data screen on the app in resistance mode, and that's what you would use for fall off potential. And you would be reporting the resistance and the error and possibly the current. And you're looking for this flat zone. So if you plot V over I versus probe distance for that rover electrode, which is this middle one here, this P2, as you go out, at some point the curve will flatten. I'm sure everyone's been hearing the term flattening the curve lately related to something else, but in this case it's not so ominous. It's the ground resistance that you're looking for that grounding grid. And if this doesn't have this classic shape, there could be something else going on at your site. So let's say your rover electrode is approaching that current, but near that current is also a fence that goes around the site and loops back to where the other current electrode is at the grounding grid, you know, like a perimeter fence. So if you're approaching a perimeter fence, which is essentially short-circuiting what you're trying to measure in the earth, you'll see a non-characteristic curve, and you can account for that potentially by moving your where you're doing that FOP test. or at least mention it in the report, because there will be some doubt as to why the curve didn't rise as you approached that C1, or you have an inflection in the middle, something along those lines. Okay, so we've talked about these 1D soundings, and there's been some questions from some end users that are very active in these types of tests. How do we account for a clay lens over the top of rock? Now the actual resistivities themselves, if you look at this model, this is a Wenner sounding. This is the measurements you take with a Wenner sounding. I'm going to show you what that looks like sped up if it were to be automated. If you had an automated type system. So I'm opening our SSAdmin program and going to the command creator, and I'm going to load what we call a command file, which is all the geometries of a sounding, even if it was manually collected. So I'm going to load and simulate a Wenner sounding. There we go. Okay, so that's actually a dipole sounding. Let me bring open Earth Imager to show you the Wenner. Okay, so you see that we're center referenced here. Hopefully everybody can see this. I'm going to try to make it a little bit bigger. Make this okay. So those black points are the electrode positions, and you can see as I step through this, we're expanding outwards. And this is what the people on the ground would be doing. Every 5 minutes, they would be moving those red electrodes and the blue electrodes out. If we were doing a Schlumberger, those blue electrodes would be staying in the same position for several measurements. And the reds would be moving, then the blue would move out, then the reds would move several times like that. So you can see there's a lot of detail here over that central position, and that's where it's sensitive. That's actually the only place it's sensitive. Let me show you what a fully automated tomography would look like. Whoops. Just need to get, there we go. Okay, so in a fully automated tomography, we have a multi-channel instrument, and it's scanning through 56 electrodes over the full space of a line. So it's giving us those transmitter-receiver positions, in this case on the outside of the transmitter dipole, and with the arrays, we typically like to use both on the outside and the inside, so like a Wenner and a dipole combined. And I'm just touching on that briefly for these next slides to answer this question about how would you account for some mixed situations. Let me go back to the slides here. Okay, so you see this layer cake geology here. this blue, this would be like a situation where you have a clay lens or clay near surface soils, typical topsoil, and then a water table, and then hard rock in that red zone. And there's a winter sounding over the top of it. That's the winter sounding. And this is the 2D model. This is not like that 1D model I showed you earlier. This is a 2D solution to that 1D data. And it's showing you the response and how only over that central position do we have any structure in our 2D model. The rest of it is very smooth, as you would expect for all of the readings being center referenced over the top there. And this is the 1D solution to that data set. Now, if we were to add a clay lens off to the side here, like you see, I need to move my screen. Okay, yeah, so this is 10 ohm-meter pockets, and this is very common to have mixed soils, and unless it's all engineered materials. But in earth systems, you very often have mixed soils, you have void spaces, things along those lines. And if you were to run a winter sounding over this area, say from A spacings from 1 foot to 30 feet, that would cover that. You would still have the same sensitivity over the middle. And this area out here, if you notice, this is the mixed 1D solution, and or the 1D data set and solution, and this is the layered only. And there is only a less than a 1 ohm-meter difference in the solution, and I don't see anything in the curve that would jump out at you that would let you know that there's these pockets of clay over there. And so that's one of the drawbacks of using one-dimensional data in typically mixed areas. So to account for it, you would have to take many sounding, many winter, hundreds of them. So in our industry, we automated it, and that's why we have these 56 electrodes scanning back and forth, so we can pick up those pockets. And this is an automated system where you lay out a cable with 56 electrodes, and then we end up imaging those. And these are actually a little bit difficult to see because they're right next to each other. It kind of amorphously, we see this smooth response, but we know there's something over there. There's something mixed over there. So that would be a good place to explore further. You would know there's something different than the rest of your site. Like this side of the site looks layer cake, and then there's something strange going on over here. And if you were running it with this method, you wouldn't know. You would be kind of blind to that type of mixed situation. Unless you happen to be lucky and have the center of your winter array directly over it. And then your narrower A spacings would respond to it. So you see the winter really is only valid over that central location. That's another important point there. So in getting into line placement, this is a power substation, and there's a high voltage overhead line going like this from left to right, and the client asked the consultant to run 2 winter arrays, and there are these red lines you probably can barely see. One of them goes directly under the power lines and one goes parallel, and they were hoping that both of these would be similar winter soundings, and they were not. Even though the winter is typically very smooth and kind of averages everything underneath that central point, this area here and this area here did not have the same values. And what it was the grounding between these towers. So for lightning protection, they are grounded to each other. So this one here is the more accurate one, the one going probably north-south or vertically here. This one is influenced by the metallic infrastructure, by the grounding between these towers. So it would have been much better if they had maybe run one over here, do some different line placement. It looks like there's quite a bit of space here, so they have other options. And so the voltage itself is not an issue. Typically, unless there's a lot of leakage from those overhead power lines, there's EM filtering, 50, 60 hertz filters, and there's also in the duty cycle of our instrument, we cancel out noise. So the EM noise from these AC power lines is not an issue. It's the grounding between the towers. So you don't want to be parallel to them. And related to that, I've created this diagram showing a static wire lightning protection and the transmission wires. This is the worst case where you're directly under and parallel between two grounded poles. What you want is case 3, ideally perpendicular to those two grounded poles. Case 1 is the worst case. Case 2 is better because you're spaced, and that 15 meters is a function of the 100-meter length of your spread on that measuring line. So keep that 15% rule in play for your project planning. And that's the slide portion of the seminar. Now I'm going to look here. We have quite a few questions. Okay. All right, we have a two-part question here. So it's related to grounding wells, and that's to get a very low resistivity. If you're on a granite dome or something like that, or top of a mountain. So they're asking if Wenner or Schlumberger would be more accurate, and that's a good question. Now, the protocol in the United States is the ASTM G57, which is the Wenner array. It's known that the Schlumberger can be more accurate because there's more unique positions possible. The Wenner requires that all 4 electrodes be moved, and I'll show you that. I'll show you that animated here on my screen. So a Schlumberger, I'll just do this for 28 electrodes. And this is a 2-dimensional one, but you see that's actually a Wenner reading. That's a Schlumberger, but we're keeping those central points at the same position and moving the outer ones like that. And there's many different steps of this. And it's expanding out. So there's many more unique positions. If I was to go to Wenner, show you that, everything is always equal. The spacing between any of the next nearest electrodes is always equal. All 4 move on every single reading. So there's not as many unique positions. The benefit of Wenner is that the signal is extremely high. You're in that in between that quarter space is a very high voltage. So the best thing to do, I think, would be to fit the protocol they're asking for these grounding wells. And then if you have a choice, consider that Schlumberger is a little bit more complicated in that you have to keep track of more spacings, and there's more chance for user error because you keep those 2 in the same spot, and then you move those out, and then at some point you're allowed to move the inner ones out, and then you continue moving the outer ones out. So communication between the staff on the ground is critical, and just double checking everything, because imagine your C1 and C2 need to be at 50 feet, but one is left at the prior position for one reading. there'll be quite a bit of error in that reading. So you need, in some cases, walkie-talkies or talking on the phone and confirming, double checking everything. Hopefully that. Now, we do have demos of our software. There was a question there. There's an Earth Imager 1D demo. Just send me an email and I'll send you a Dropbox link or something. That's quicker than going through our request system. What will the maximum subsurface penetration depth be if we use 20 electrodes using a dipole-dipole arrangement for an IP survey? Okay, that's a little bit off topic, but it does relate to electrical methods in general, in that for a single line, your exploration depth for these types of arrays is generally 15 to close to 20% of the line length. So whatever your spacing is on those 28 electrodes, that will determine your exploration depth. And your line length is also a function of any kind of interference you may have from ground to metallic infrastructure, from as mentioned from the slides on the presentation there. What if we have underground or overhead power lines parallel? Okay, that's the same. Yeah, okay, that's that slide. Going perpendicular or being spaced off. There's a measurement. There's a type of measurement actually, which I did not mention, the reciprocal, and I really should. Now that is something I added to our help desk, and I'm just going to show you our help desk really quick because it has a nice diagram for that. The theory of reciprocity is very helpful to determine noise levels, and it's a reciprocal check. So for Wenner, we have A and B on the outside and M and N on the inside. That's C1, C2. If you were to swap those on the faceplate of the instrument, you don't have to go out there and move it. You should get a V over I that's well under 10% different. If not, most likely one of those wires is leaking, because you're much more likely to leak on the high voltage, high current transmitter positions. The receivers will receive the signal you're intending, and if there is leakage, maybe some additional noise, but they're much more likely to be a problem when they're acting as transmitters. So the fact that you're swapping those positions lets you know if there's an issue in your cabling. It also will more accurately measure any spurious noise, which you may have in one position versus the other. But that's generally handled by repeats, the spurious noise. It's much easier to do that way. So the reciprocals would be helpful if you're questioning whether you have noise from very high voltage, maybe a bad transmission tower that's leaking into its grounding system. That's rare, but it can happen. Simulations of resistivity. Yes, so in this presentation, I used a priori models, like a layer cake model, and then the model with the little clay lens off to the side. You can do that with Earth Imager and the 1D and the 2D. If you know what kind of porosities, if you do some petrophysics and you know how much resistivity would change for a given porosity, you can input that resistivity. Our modeling code doesn't take engineering soil properties like porosity or plasticity or compaction. It doesn't have those additional physical properties. It's specifically solving for resistivity. The gauge of the wire. We actually recommend 18 gauge wire, not 12 gauge wire. The losses are reasonable. If you use good copper stranded 18 gauge wire, you should be fine for thousands of feet. That's a question there. Our cable reels are designed to be easy to use and to eliminate noise. They're shielded, and you need to, if you're just using a cardboard spool, you have to unspool all of the wire off of it, for example. But if you're using AGI reels, you're good there. RMS, root mean square error. For field repeats on the V over I, it would be pretty extreme to have a 10% repeat error. I think 5% is reasonable. It's a site-specific issue, but the default on the SuperSting is 2% standard deviation. Okay, just a second here. Looks like I'm okay here on sound. Someone said they lost the sound. I mentioned CDAGs. Are you working with SES at all, or bringing in 2D or 3D ERA into the CDAGs for more accurate modeling? We would like to be involved with that, and we're going to reach out. There was a modeling code shootout at one of the CDAGs meetings that I went to. They had 5 different codes. So having more layers, they were only using 1, 2, 3 layers in their models. That would be important. Okay. Preferred method is again the generator with the AGI generator power supplies, simply because it's lighter versus the deep cycle marine battery. The default is to use the deep cycle marine battery. That's out of the box. There's an additional accessory if you want to run the generator. You do not want to take the 12 volt off of something else, such as the 12 volt directly out of the generator. That would cause a problem. The SuperSting has a very dynamic power draw, anywhere from 15 watts to 900 watts back and forth as it auto ranges its output current. So you need to use certified the inverters we manufacture here on site in Austin. We manufacture everything on site, from the small component on up to the finished boards. And those are tested and approved. So I would use those if you do have a small 900 watt generator. There was a question about radial winner. That is for, it is a 1D method still, so you have those issues that I mentioned, but it can give you some anisotropy, but it won't let you know if you have heterogeneity. So radial soundings are still an issue there. It's best to do a 3D survey if you're interested in fracture direction and things like those. 500 feet deep, what would be the best equipment? If you're going 500 feet deep, I would recommend the SuperSting, because the A spacings are getting up there. But you could certainly do it with the mini Sting as well with the boost battery. So you're right at that 500 foot. I would if you have a SuperSting available, I would use it. For a small A spacing of 3 feet and less with 15,000 to 100K ohm foot soils, tips for getting a reading, not INOVL. Okay, Michael, yeah, that's a very good point. I actually added a help desk article for that. And if you type in narrow spacing, there's a walkthrough for this. And go, let me clear this out here. It's manually adjusting the current and the voltage. So the SuperSting is a very high power instrument. If you're running at like half foot spacing, you can saturate the P1 and P2. So there's an additional step where you manually step it down so the auto ranging is closer to the ideal value of these very narrow spacings. And then you should avoid the, start off by just reducing the current and then see where it solves, because it's solving for the ideal current during auto ranging. So if you set the current down to 250 and it transmits, it still gives you an INOVL, then lower it to 100. If it transmits at 90, then you really should have it be at 150. So you see, you don't want to brick wall it. So there's a little bit of trial and error if you're having that extreme case with narrow spacing. So that's very narrow spacings with a supersting. That's how you would solve that issue. Superstings have a calibration interval of 1 year, and we have NIST traceable capabilities at AGI. So and we do have free loaners for owners of superstings now. So they can send one out if you're shipping yours in at no cost if you cover the shipping. Wire suggestions again: 18 AWG or about 1 millimeter conductor, copper stranded, with a polyvinyl jacket is sufficient. Oftentimes it's I can send you further spec if you want. It's what we use on our reels. Now a cliff edge, that's a that's topography, which is not accounted for in 1D soundings. So if you're talking about 2D, send me an email and we can go into that. But you're talking about a cliff edge, and in that case, if you're doing 1D and you want accurate results, you should go perpendicular to the cliff edge, because topography is not accounted for in these type of resistivity tests. How far apart should lines be in 3D? Same person. Yeah, we're venturing outside the scope of this particular set of topics with this 3D question, but I can help out with that in another webinar. And sensitivity is roughly 1/2 of your electrode spacing. That's for all methods. So your resolution is roughly 1/2 of your electrode spacing, and then lateral resolution needs to be 2D or 3D methods, and that's why I went into those slides at the end there. So it looks like I covered all of these questions sent. And if you have any others, feel free to reach out. Thank you guys very much for attending, and I hope everyone's staying safe out there. And we'll try to do more of these webinars. And yeah, and hopefully my home office here was not too distracting. But thank you guys. Bye.